I would like to solve now is exactly the similar problem, right? For considering like two wires carrying current, and now I'm going to calculate the what is the forces actually one wire is going to generate on the other wire, right? So if you have, for example, if you have this wire to here, like with a current through it, is going to generate a magnetic field, as you can see here in blue, right? And this magnetic field is going to interact with the current in this first wire, and is going to generate a force here. Of course, because of Newton's second law, we have also this wire here, the first wire, also is going to do the same. Is going to affect the second wire the same way. But I no need to prove that. This is easily verified because of Newton's second law. Interesting things to say here: if you have currents in the same direction, what is observed when we have one experiment with this kind of arrangement, you see that is going to generate attraction forces. So let's put here E1 and E2 same direction. If they have same direction, like this, so what you have here is attraction. And if these currents here, if they have, maybe where to put the I sub 2, if they have opposite direction, though this is repulsion. Here, this, for example, have something like this, and the other ones like this, for example. Okay, just let's keep in mind that we learned last class. Let's go back just to remind us what we learned. What is that? Lecture 8. We already know, right, the force generated in a wire, right? You have this expression here is going to be the current times the length as a vector form, and the vector product between the length and the magnetic field itself. So let's go back to our current class and let's write this down. So this force 1 here, right, can be actually written as L times this magnetic field, but the magnetic field this wire here. So all you have to do is actually write those expressions here. We know that actually, recalling the results that you got from the previous examples, right? We know that actually this one, the B2, is going to be me0 I2 over 2 pi a 2 pi a. And this direction is radial, right? You can actually see that this vector product here is going to give something. I'm not going to prove here, guys. So the magnitude of this force 1 here is going to give us, actually is going to be the product of these two currents, I1 I2 over 2 pi a. And this times the length L of this wire. Okay, this is very known. Actually, most people actually learn this expression in high school, as far as I remember. But it's also very common also to rewrite this equation here actually in terms of the force per length, because why this is important. Actually, we learned this in high school, but what is most common here for us is actually to represent this force here between the, and of course if you're to write the force F2, right, it would be exactly the same if you're going to write the force F2 here, would have exactly the same mathematical form like this one. But what is most interesting is this one, to write this normalize this equation by length. My god, what the hell. Let's normalize this. And why is this so important is actually this is used to actually to calculate, to define, not calculate, to determine one of the SI units. Not one, two actually. We can define two from this definition here. We can define actually two of the SY units. I wrote here for you guys. Look, the force between two parallel wires is used to define the ampere as follows. When the magnitude of the force per unit length, this one that we just wrote here, right? I mean the left hand side of this expression. Force per unit length between two parallel wires that carry identical currents and are separated by 1 meter is 2 times to 10 to minus 7 Newton per meters. The current in each wire is defined to be 1 ampere. And similarly, we use exactly the same to define 1 coulomb. I don't know why I didn't write here. Man, okay, but just for you guys to know. So this is one major relevance behind this expression here. And this is also very common in problems. I solved one problem for you here, guys. I don't know if you have time. If you have time, I'm coming back and I'm going to solve this problem for you. That is the problem 41. If I don't have time, I'm going to leave the video for you guys in our web page later. But I don't know if we have time. If we have time, I come back here and I'm going to solve it. But it's just one application, right? How to apply this, what we just learned here, in a problem from the textbook. Let's see some simulation here, guys. La, 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 la. Is it working? Oh, look. Okay, simulation, very nice simulation from Barb Newitt. As you can see here, if you have currents in the same direction, you have forces generated on the wires that are attractive, right? There are attraction forces. And if you have opposite, let's see, let's put negative sign. Do you have negative here? Oh no, we don't have. Can I have? No. No, this is the distance. Okay, let's keep 2. And let's make this negative. Oh yeah, you can make negative. -4. As you can see, we have repulsion forces. She even put here, so this is you can see that actually on the left side of the wire A, we have the magnetic field actually piercing out of the plane of the screen, and on the right side is actually piercing in the direction of the direction formed by the plane of the screen. Okay, very nice. I will leave this for you guys. You can actually use you can actually play with this simulation later. Okay, that's all I want to say now, and I would like to move to the next part of the class where I'm going to show you Ampere's law.